We have seen that a band limited signal, which is also constrained to have some mean square value, for such a signal, white Gaussian signal has the largest entropy per second. And we have also seen that mutual information for a continuous channel, which is I x colon y is equal to differential entropy of the source minus the conditional differential entropy of the source, given that you have observed y as the output of the channel on which this transmission of x has taken place. Now, today we will try to find out capacity for a particular specific channel. We have also seen that the capacity is the maximum of this mutual information, and we also seen that this for a given channel, this capacity turns out to be the function of the input PDF fx. Okay. So, now our problem is to calculate the capacity of a band limited additive white Gaussian noise channel. So, our first assumption is that channel is band limited, and let us assume that this is band limited to B hertz and it is disturbed by additive white Gaussian noise with power spectral density given by italic n by 2. We also assume that the signal power is constrained to a value which we call it as P average. So, the disturbance is assumed to be additive. So, the received signal, which we call it as yt, would be given by xt, which is the input signal, plus noise, which we denote by nt. Now, all these are random processes, correct? Because our channel is band limited to B hertz, it implies that your noise process will also get band limited to B hertz. Your input process, when it is passing through the channel, will also get limited to B hertz, and obviously your output yt will also get band limited to B hertz. Okay? Okay. Now, the channel capacity is by definition the maximum rate of information transmission over a channel, and the mutual information we have seen turns out to be this expression. This we have justified this in previous class, and we have also shown that your mutual information is symmetric with respect to x and y. So, I can also write this as Hy minus conditional entropy of y given x. Whenever I say entropy, basically it is presumed that it is a differential entropy. Okay? So, the channel capacity C is the maximum value of this mutual information. Now, let us first find the maximum value of mutual information per sample. Okay. So, we will try to do this assuming that the channel is band limited to B hertz and disturbed by a wide Gaussian noise of power spectral density italic by 2. Right. Now, this Yt is equal to xt plus Nt. All these signals are band limited to B hertz. So, all these signals can therefore be completely specified by samples taken at the uniform rate of 2B samples per second. And the problem is to find out the maximum information that can be transmitted per sample. So, let us use x and y as sample values of xt, nt and yt respectively, right. Fine. So, the information, that is your mutual information transmitted per sample is equal to, we will use this expression for computation because it is easier to do that. Okay. Now, your conditional differential entropy is equal to joint PDF log to the base 2 of 1 by conditional PDF and integrated over x and y. And this can be written as follows by Bayes rule. Sorry, this integral we are breaking it. Fine. Okay. So, now we have also said that the sample values of these random signals we are going to denote as y, x and n. So, we will get y is equal to x plus n. Hence, the PDF of the random variable y when x is given is obtained as follows. Therefore, PDF of conditional PDF of y given x will be the same as the PDF of the noise except for the translation by x. So, this will be equal to this, okay, because y is equal to x plus n and x has been given. So, the PDF of y given x will be equal to this quantity, which is the PDF of the noise except for the translation by x, okay, where your Fn is PDF of the noise sample. Therefore, let us evaluate this integral. This we can rewrite it as okay. Just substitute z equal to okay. So this is some z equal to y minus x. Right. So if I do this and substitute into this, I will get it as this integral now. This by definition is the differential entropy of the noise samples. We get conditional differential entropy equal to Hn integral of fx dx. This by property of the PDF is equal to 1. So, this is equal to Hn. Now, this relationship is applicable to all types of additive noise. No assumption is made about the noise except it is additive. Okay? Therefore, your mutual information is equal to Hy minus Hn bits per sample. Now, our y is equal to x plus n. We have assumed that the mean square value of the signal xt is constrained to have a value p average, and the mean square value of the noise is, let us assume, to be np, and let us assume that this signals xt and nt are additive, that we have done, are also independent. Correct? So, what will it imply? That this sample x and n random variables will also be independent. So, if that is true, then we can find out the mean square value of this random variable y will be equal to the sum of the mean square value of this plus the mean square value of this, because they are independent random variables. Okay? So, this will be equal to this value. So, this is your noise power and this is your signal power. Fine. So, for a given noise, obviously your differential entropy is given. So, in that case your mutual information is a maximum when Hy is maximum. It comes from this. This is given. So, this will be maximum when this is maximum. Now, we have seen that for a given mean square value of y, which is equal to P average plus noise power, H y will be maximum if y is Gaussian. This we have studied earlier, correct? So, it is important to know this, right? So, Hy will be maximum if y is Gaussian, correct? So, what this implies that your maximum value of that if y is Gaussian will be equal to half log to the base 2 pi e power signal power plus noise power. Okay. Now, y is equal to x plus n. This we are assuming it to be Gaussian, and if you want y to be Gaussian, only if x is also Gaussian. Okay. Now, because mean square value of x is P average, which we have assumed, therefore, it implies that the PDF of my x should be given by this Gaussian PDF, which will be equal to this expression. Fine. I max, which is equal to H max y minus H n is equal to now half log to the base 2 pi e power average plus noise power minus differential entropy of noise. So, for Gaussian noise, we know that differential entropy is equal to half log to the base 2 pi e n p. Okay. Now, remember the noise power, correct, will be equal to the power spectral density of the noise multiplied by the twice into the bandwidth of the channel. It is a band limited. So, this turns out to be this value. Okay. So, what happens is that from this we get the channel capacity per sample as follows. Bits per sample, Now, if all the samples are statistically independent, the total information transmitted per second will be 2b times this value Cs, correct? So, now channel capacity C represents the maximum possible information transmitted per second, correct? So, then I can write that C is equal to twice B multiplied by this value, which is the capacity per sample. So, remember that samples of a band limited Gaussian signal are independent if and only if the signal power spectral density is uniform. Is uniform over the band. Therefore, the information can be transmitted at the maximum rate when the power spectral density of signal Yt is also uniform. Okay, fine. So, therefore, transmission of information at the maximum rate implies that the power spectral density of signal Yt is also uniform. Remember, because the power spectral density of the noise is flat, is white, correct? And we want this relation to hold good. So, it implies that your Y being Gaussian should also be flat, the power spectral density of that, correct? Fine. So, this implies that the power spectral density of xt must be also uniform or it must be flat. Okay. So, quickly recapitulate, y is equal to x plus n implies that power spectral density, this here f denotes the frequency, not to be confused with the PDF please, would be equal to this, because we are assuming it to be additive process, correct, and we want this to be white, this is already given to be white. So, it implies that power spectral density of xt must also be uniform and we have also seen that xt has to be Gaussian. So, it implies that xt is also white Gaussian signal. So, to recapitulate, when the channel noise is additive, white and Gaussian with mean square value say NP, correct, and that is the power which is equal to power spectral density of the noise multiplied by twice the bandwidth of the channel because it is limited to B. So, when the signal noise is additive, white and Gaussian with mean square value, the channel capacity C of a band limited channel under the constraint of a given signal power P average is given by this following expression. Bits per second, where B is the channel bandwidth in hertz. So, this is the maximum rate of transmission which can be realized, and this will happen when the input signal is a white Gaussian signal. Okay. Now, let us see what happens to this capacity when I change the input parameters to the channel. For example, if I increase P average, what happens? From here it appears that capacity will increase, okay, and so that is fine, that will happen. But what will happen if bandwidth of the channel increases? If the bandwidth of the B, that is B, increases to infinity, will I get channel capacity also to be infinite? This is a question which I have, and we will find out the answer to this in the next class. Thank you.